Great. So I think Daniel is on the line and we have a shared set of slides that hopefully he can bring up. I am wonderful. Thank you, Daniel. And I don't know if I have control over these. So if I ask you, you might have to change slides. So I'm going to give a brief overview of what we're doing. And then Daniel is going to dive into some of the details on what we've been working on so far. As was just mentioned, we're using data from TESS, Transiting Exoplanet Survey Satellite, to look for anomalous variability from basically tens of millions of main sequence stars. And let's see if I can change this. Perfect. So this is a recently funded program through the NASA XRP. And I'm the PI, and Daniel is the lead postdoc who's been doing a lot of the work. But we have many folks on as co-Is who are listed here on the screen, some of which are affiliated with the Breakthrough Listen program. And we've had the pleasure of having a number of students, current and future, coming on this summer to work with us. So, oops. Change the slide here. There we go. So we're motivated by some serendipitous discoveries. The most famous one of which was just mentioned, that's Boyagin's star, which in brief was a target of the Kepler mission. And it was photometrically monitored for several years during the Kepler main mission. And what was seen was this very interesting light curve. So here we have many hundreds of days on the x-axis, and the flux, you can see there are these sudden plunges in brightness down to about 10 to 20% at a time. And initially, people wondered what on earth could this be? There were many theories put forward. I think we now believe it is some sort of astrophysical origin, perhaps a family of comets. But at the time when this discovery was made, it was also, the idea was put forth that perhaps this object could be surrounded by some kind of artificial structures. And here is an artist's conception on the right of something akin to a Dyson sphere, where you may have an advanced civilization which needs to either harvest energy or carry out some kind of communication activities by surrounding their central star with semi-opaque structures, which then in rotating around that central star periodically or even aperiodically occult it, creating these brightness dips. There were a few other interesting objects discovered over the course of Kepler and its subsequent K2 mission, one of which is this light curve here called dubbed the random transitor, which didn't seem to be some kind of exoplanet because the fading events were not at even intervals. So there were a few fascinating things found by Kepler among the several hundreds of thousands of stars observed, none of which was concluded to be artificial in nature. But we got to thinking, if there are artificial structures out there created by some civilization, what would it take to actually detect them? And the first thing is that we really need to observe many, many more stars than Kepler did. And so we have been, let's see, change the next slide here. Daniel, can you do that? Perfect. So we've been really blessed with this onslaught of data from the TESS mission, which differs from Kepler in that it's monitoring nearly the entire sky. It's not going as deep, so the stars aren't as faint. Many of them are roughly binocular brightness, but the field of view as it moves from one section of the sky to the next with its four cameras is much, much bigger. And therefore, it looks at many more stars, albeit for shorter periods of time than Kepler did. So the gist of our project is to use the first couple years of the TESS mission for which there are what's called the full frame images, one of which, a portion of which is displayed here. And you could just see all those pinpoints, how many stars, and that's just a tiny, tiny bit of the data. And from those full frame images, our team members have created light curves for roughly 60 million stars for the first 2 years of the mission. There will be more of that if we incorporate the third and the upcoming fourth year at 30-minute cadence for roughly 1 month each. We also have a lot of other information on these stars since they're roughly, since they're quite bright, so we can get photometry, temperatures, and kinematics from the Gaia catalog. So what we are aiming to do, and I should say this project is really just getting underway in the last couple months here, is to use machine learning to look for anomalous variability, whether it be of the form of Boyajian star or something completely different. Here are some example light curves of objects, which Daniel can tell you more about, but he did a pilot study with the Kepler dataset to use machine learning to find oddball behavior that didn't necessarily match up with what the other stars in the data set were doing. And he's going to tell you in a moment more of the details of how we go about doing this anomaly detection. And this is an area of machine learning that's a subject of much development. If you've ever got a call from your bank that there might be some fraud on your credit card, that's a form of anomaly detection. We're doing it with stars. We want to detect variables and cluster them together into various types, whether they be pulsators, eclipsing binaries, star spots, and then find the things that don't match that and follow them up. So our goals are to either detect a transiting megastructure or more likely put the strongest constraints to date on their presence around main sequence stars. We hope to find some interesting targets if we get any anomalies to pass off to radio searches. And then alongside this, I'm not really going to go into detail, but there's a whole nother side of our project where we're looking for occulting material that is astrophysical in nature, such as comets, to constrain also the presence of rocky, smaller than planetary debris around these stars. So it's really I like to call it a needle in a haystack search. And there's sort of this whole sequence that Daniel will tell us about, going from light curves to looking at sort of how normal, in a sense, the data is. Then we pull out the oddball things, we cluster the types of variability, and also do a targeted search for occultation signals, which we can, using our imagination, simulate to some sense. And then once we find interesting objects, we have plans to follow them up. Okay, so I'm going to hand it over to Daniel now just to tell you a bit about what we've done so far and exactly how we're manipulating the data. Daniel?
Hello. Thank you for that wonderful introduction. Going back just one slide for a moment. So this is our general process, and to date, we're kind of in the second step, third step area, where we're trying to identify all of the weirdest things, because most of the stellar targets are going to be fairly inactive, and we want to focus very much so on the ones that are more interesting. And we imagine if we have any form of technosignature available, that it will be an exotic signal of some type. And also going through this sort of process, with the 60 million light curves that we've got, we obviously can't go through each one of those by hand. So we really need to focus the search as we kind of like narrow down in each one of these steps. So going from the 60 million light curves down to fewer and fewer, so maybe 100,000 light curves, maybe down to 10,000, down lower and lower until we get to a manageable amount of light curves that we can actually follow up, either with a manual observation, like additional telescope observation, or other such, maybe just going through the data and identifying different artifacts. So first, where we're looking for these anomalies and trying to identify the weirdest stuff. So what does it mean to be weird? So the types of things that we expect to find, that I found in kind of the pilot study during my my PhD work, was new examples of rare events, corrupted data, so artifacts that don't represent astrophysical variability, but which will still be, you know, weird. It's a technosignature of sorts, just not one we're interested in. And then what we are interested in is the new undocumented phenomena, the weirdest stuff that doesn't have an explanation to date. Maybe it's a new example of a rare event, but a rare event we've never seen. So it's something undocumented, something we don't have an example of. In order to do this, we take these light curves, which have thousands and thousands of observations, and we want to be able to kind of standardize this approach, since different data have different systematics. With TESS, they have different durations between sectors, just by a couple data points, really. But one thing we do for this anomaly detection, since we're interested in astrophysical variability, is to parameterize these light curves into what we call features. So it's essentially a dimensionality reduction where we focus on things that describe variability above anything else. So examples of these features are maybe spikes in the data, so quantifying the number of spikes, how high they are, the shapes of peaks, if there are peaks, and very importantly, periodicity, if any exists. So those are just a few examples of the features that we look at when we're looking for weird things. So that as we define features, as we define an anomaly, the anomaly is going to be an anomaly based on these features, based on these different things that we define as metrics of interest. As we do this, we score each one of these things based on that feature space, where it falls in that feature space. So we use a density-based approach where we put these points into this feature space, and then we see how close it is to its other neighbors. And based on how close it is to its other neighbors, we evaluate its normalcy. So in bright yellow, we've got maybe 99% of the data is tightly clustered, all very, very close to one another. And then maybe 1% of the data kind of spreads out over the entire space. And we can then define what it means to be normal. So if we just kind of look at a plot of score versus rank, we can find this elbow and say everything above this line is weird, everything below this line is normal. So that's kind of a nice little threshold cut, which we can make so that we focus first on the weirdest stuff. And when we do that, and we just kind of like go through and we look at some of these things kind of randomly, what has been determined to be an outlier, we find just some funky signals, stuff that isn't quiet. And maybe I should provide a plot of a normal light curve, but imagine, if you will, a line. And that's what a normal set of data looks like. It doesn't have any notable features. The variability is just focused around this. It's been normalized so that flux is at 1. So the median flux is at 1. So a normal data point will have like maybe 0.1% variation from this median of 1. And what we see in these outliers are some weird, or at least maybe not weird, but interesting, or at least we see variable activity. And then we see other types of other classes, which we know but are, relatively strange because essentially all variables that we see in TESS with variable classes are quote unquote weird. At least they are rarer than inactive stars or low active stars. So just kind of more samples of these outliers, different classes of variability, which get highlighted. So I guess the moral of these two slides is that we haven't yet found anything which we're actively following up as something we have never seen before. We're mostly dealing with artifacts and known types of variability as of right now. And in order to make sure that our methodology is going to find something like that, we've also been working with students to do signal injection to see if we can put light curves in, which will have features that we expect a technosignature might have, and see if we will recover this. So we haven't done this injection quite. We haven't put these light curves into the anomaly scoring quite yet, but we have injected the signals. And we will be working with Joshua Bromley over the summer on doing this even more so. Actually getting them in there, making sure that the scoring works to find what we would expect to be a technosignature instead of just, quote unquote, just variability from astrophysical objects. Additionally, we're exploring the utility of clustering data as opposed to just anomaly detection. So it could be that any types of signals we're looking for will be clustered tightly together with like objects, even if we haven't seen it together. So this anomaly detection might score something very, maybe not very low, but like lower because it's closer to similar objects. So we're playing with clustering, which each one of these light curves in the different plots are different objects. So these four all seem to have very similar periodicity, very similar transit depths, but they're all different objects. So we're seeing some promising results from clustering where it will tightly cluster these very similar objects together, and we can explore these different clusters in depth. So we're exploring that, and we're also playing with classification, which we hope to work with a student over the summer through Berkeley. So this is just kind of a proof of concept to see if we can sort things into very kind of broad bins of pulsators or binary objects or miscellaneous. And we're seeing 93% correct classification based on the classifications that we have, which are limited and fraught since these classifications come from SIMBAD, but promising early results that we will pursue with student involvement as well. So all that to say, we're still kind of in the early steps, these first 3 steps of kind of defining exactly how we're going to be paring down the data. So we're looking more and more closely at fewer and fewer objects. But the progress is promising, and we haven't hit any major roadblocks as yet. The more we go down this rabbit hole, the more we will have to present, hopefully. And in addition to just having these ourselves, we work with some students over the past semester to start forming a database, a value-added database, where it will make follow-up a little bit easier, where we have an image of the light curve itself, supplementary data, and just additional information which will facilitate this sort of follow-up, but only for the highest ranked outliers. So all of that is in progress, and we are moving forward, inexorably forward. So thank you.